All right, so just a really quick review. We talked about pH at the very end of the last lecture, but basically pH is a nice little way of expressing a solution's acidity or basicity, okay? So what we do is we just use this equation. Make sure you guys are comfortable with it. You have it either memorized or written somewhere because we'll be using it a lot. But pH is basically just equal to the negative log of the concentration of H plus ions or protons inside the solution, okay? So in a neutral solution where it's 1 times 10 to the negative 7 for the concentration of H plus, it will equal 7. So 7 is kind of the baseline. That's when a solution is neutral. So pure water is neutral. Any number less than 7 on the pH scale is acidic, and anything greater is basic, okay? Make sense? Kind of a review from last time. Again, you just take the concentration or the molarity of H plus, and you just put it in here, negative log. Okay. All right, so we got a quick little picture of the pH scale. Okay, and so we got some examples of things on the pH scale. So water, pure water is 7. Milk is a little acidic. The greatest drink in history is a little bit acidic, and then so on and so forth. Black coffee. Yeah, black coffee. See, once you put stuff in there, it's not good no more. Yeah, you want it exactly the way it is. Okay. Anyway, so yeah, this is the pH scale. Again, if you get numbers that are greater than 7, just know that it is basic. If it is less than 7, it is acidic. Just to let you guys know, you guys might see it on a problem or two throughout the year, maybe not on the test. But there are negative pHs, and so that means since it's smaller than 7, negative pH means that it's like super duper acidic. Okay. Yes.
Wait, so it's anywhere in 7 neutral, or is it like only 7 flat?
7 flat is neutral. If it's like 6.8, 6.9, that'll be a little slightly acidic. Yeah.
It's like 7.2, you say slightly basic.
Slightly basic, yeah. Exactly. Good question. All right. So whenever I go to the mall with my wife and I see a really basic girl, I see she's pH 14. And then she's like, and my wife's like, okay. Anyway. All right. So I'll give you guys a quick minute to find out the pH of these solutions. So we got first lemon juice. So obviously this is acidic, but I want you guys to calculate the acidity. If lemon juice has a H plus concentration of 3.8 times 10 to the negative 4. And then the next other one, part B, I gave it to you in the concentration of hydroxide. See if you guys can figure out the pH of that solution. Just keep in mind that it's hydroxide concentration here, okay? So you'll have to take that into account. So I'll give you guys about 2 minutes to do that, and then we'll go over it together. Okay, so for part A, it should be pretty simple. All we're gonna do is plug in this value into the pH formula. So for part A, we'll just need to do pH is equal to the negative log of this right here. So it'll be 3.8 times 10 to the negative 4. And that should give you a pH of, hold on, I wrote it down very wrong. Where's my calculator? I'm a mess. What did you guys get? 3.42, good. That sounds about right. Okay, and it makes sense because if it's lemon juice, it's probably acidic. So you want to make sure it is less than 7. Okay. All right, let's go to part B now. So for part B, you have the hydroxide concentration. So you can't just plug this in exactly the way it is. Instead, hopefully you guys remember from last time that the concentration of H plus and hydroxide is always going to equal 1 times 10 to the negative 14. And so you'll just have to plug in your values for that to calculate for H plus. Okay, so the concentration of H plus will be equal to 1 times 10 to the negative 14 divided by the concentration of OH minus. So 1.9 times 10 to the negative 6. And that should give you a value of 1.3 times 10 to the negative 9. What's up? Did I say 5? Oh, 5.3. Sorry, 5.3 times 10 to the negative 9. Sorry, my bad, guys. I don't know what I'm doing no more. All right, and so this is going to be the concentration of H plus. Okay, and then from there, you can just plug it straight into the pH formula, and that should give you a pH of about 8.3, something like that. Okay. All right, any questions? Not too bad. Okay. Yeah, so if you ever get OH, then you can just use this right here, this equation, to solve for H plus. Okay, but there's actually an easier way to do it, which we're gonna go over in a second. Okay. But this makes sense so far? All right, so pH is the most common way to talk about, the acidity or basicity, but I actually think it's very inferior to the next one we're gonna talk about. And the next one that we're gonna talk about is POH, which I think is the best way of measuring hydroxide concentration, because that's my initials. But anyway, but we don't use it that much. But you do need to be aware of it, because sometimes you will have questions where you need to find POH or you're giving something in POH. But POH is, if you guys look at it, it's the exact same thing as pH. It's just with hydroxide concentration instead of proton concentration. And it's just the exact opposite of the pH scale. So 7 is still neutral for POH, but this time anything less than 7 on POH is basic. Anything greater than 7 on POH is going to be acidic. So it's literally just reverse of the pH scale, okay? There's also pKw, which is the negative log of KW, but you very rarely see that. But just keep that in mind. Basically, if you see P in front of any variable, it's just going to be the negative log of that variable. Okay. So just keep this in mind. This is an important thing.
Wait, so less than 7 is basic?
Less than 7 is basic, yes. On the POH scale, which I think makes a lot more sense. No. I just think this is a superior scale. I want all of you guys to just write POH, no pH. T. Don't worry about it. It's tyrant. Paul the tyrant. Oh. All right, so one quick relationship that I do want to teach you guys, because this will be helpful. This part you can ignore, is this right here. pH and POH will always equal 14 at 25 degrees Celsius. Okay, but usually we'll be looking at stuff in 25 degrees Celsius. So this actually makes our problems a lot easier to solve, because remember how earlier you were given the OH concentration, right, of a solution? So in the previous problem, yeah, OH concentration was 1.9 times 10 to the negative 6, right? Okay, now instead of doing the KW 1 times 10 to the negative 14, you can literally just find POH and then just subtract it from 14, and that'll give you your pH, and you should get your same answer. So this is a quick and easy, real good relationship, a real useful relationship you can use to easily convert between pH and POH. Okay, so just keep that in mind. All right, so let's do this really quick question. Okay, so what is the pH of a solution that has a POH of 14? So POH of 3. So if POH is 3, what is the pH going to be? 11, yeah. Okay, so this solution, if there's a solution like this, POH is 3, that means pH is 11. And then, what do you guys think? Is it acidic or basic? Basic, yeah, it's going to be basic. Okay, remember, yeah, 7 is, or 11 is greater than 7 on the pH scale, that's basic. And then this is less than 7, so that's going to be basic on the POH scale. Yeah, so I think personally, it's best to just pick one of these to think about. I personally just think about the pH scale. And if it's greater than 7, it's basic. And if you ever get POH, I mean, if you can instantly think about it, that's fine. But just to double check your answer, I just always go back to pH. That helps me figure out if it's acidic or basic. Okay. Any questions? Easy peasy. pH. Okay, let's move on to this next question. Okay, so I am going to give you guys about 3 minutes to try both of these, 12.17 and 12.18. 17, you're gonna be calculating the H plus concentration of apple juice, which has a POH of about 10.24. And then for 12.18, I want you guys to find the OH concentration of an antacid tablet, which has a pH of 9.18. Okay, so just more of the relationships we've been talking about, just giving you some time to practice converting between them. So take about 3 minutes to do that. We'll go over it together and we'll move on to the next thing. Yeah, there are multiple ways to do these, so you can use whatever method you think makes sense most to you. Okay, so let's start with 12.17. It says that it has a POH of 10.24, and we're calculating the H plus concentration. So like I said, there are multiple ways to solve this. So if you don't do it the way I did, but you get the same answer, you're totally fine, okay? So since we have POH, but we're looking for the proton concentration, I'm first going to start off by converting this into pH, okay? So we know that pH and POH, when you add them all up together, that's going to give you a total of 14. And so if I wanted to convert this into pH, we can just rearrange the equation, which is going to be 14 minus the POH, which is 10.24. And so that will give me a pH of 3.76, okay? Now, based on this, we can use the pH equation. pH is equal to the negative log of the H plus concentration. And so what we want to do is we want to isolate the concentration of H plus. So I'm going to plug in 3.76 is equal to the negative log of the H plus concentration. Now we need to get rid of this log. Okay, so if you guys remember from your algebra classes, if you ever want to get rid of a log, well, first thing we need to do is we need to move the negative to the other side. I'm going to do that. But if we want to get rid of a log, what we can do is we can put everything, you can do 10 to the power of all that stuff. 10 to the power gets rid of the log, and that's going to end up with, you're going to end up with H plus concentration on one side, and then you'll have 10 to the power of negative 3.76. And that's how you can get rid of a log in order to figure out H plus concentration, okay? So from there, we can just simplify that, just punch it into your calculator, and you should get a concentration of about 1.74 times 10 to the negative 4 molarity. Okay. That's one way you can do it. You can also keep it POH and at the very end use the 10 times 10 or 1 times 10 to the negative 14 value to convert it, but either way works as long as you have something like that. Okay. Any questions or not too bad? Okay. Guess I'll just talk to myself. At this point. Okay, same thing for 12.18. So I'll go through this one very quickly. So here you have pH of 9.18 and you want to find OH minus. Okay, so what we can do is basically the same thing. We can use the relationship. pH is POH is 14. And then you can find out that POH is going to have a value of 4.82. All you need to do is 14 minus that. And then same thing, POH is equal to the negative log of the concentration of OH minus. You're just going to plug this value in right here. And then from there, you just do negative 4.82 equals log of OH minus. And then you just put it under 10 to the power of all that stuff. And so your concentration of OH minus will be equal to 10 to the power of negative 4.82, which is going to be 1.5 times 10 to the negative 5 molarity. Okay, something around there. Okay, so the key to figuring out this log stuff is to just remember you can get rid of a log by putting it 10 to the power of that stuff. Okay. Isn't math fun, guys? It's exhilarating. I feel most alive when I'm solving these problems. It is a little depressing, but you know what? Report me for doing math. Math, yeah, that is a little bit weird. That's what Asian parents expect, you know, even though they hate it. Anyway, let's move on. Okay, so there's a lab techniques on measuring pH in a lab setting. We'll be doing this with our titration lab later, so we'll talk about it more in depth when we do that titration lab. But for now, I know you guys all keep up with the reading, and so you guys will probably read that then, okay? Just keep that in mind. But you should read through this because this is pretty important, and it will probably be on the AP test if there is an FRQ question about titration or something like that. Okay, so just keep that in mind. Okay, let's move on to the next section. It's about strong acids and strong bases. We briefly touched on this last time. Okay. But strong acids, let's talk about them. Basically, these are strong electrolytes, and that means they break apart almost completely inside of a solution. Okay, so if you have a strong acid or strong base, they basically dissociate completely. Okay, it's like I said, it's like Taylor Swift breaking up with a boyfriend, never getting back together, like ever. Okay, so that's basically what they are. So just keep that in mind. Strong acid, strong base, they never get back together. All right, the seven common strong acids that you guys need to memorize are these ones right here: HCl, HBr, HI, HNO3, HCl3, HCl4, and H2SO4. Okay, so highly recommend that you memorize it. It'll be very helpful when you guys are taking your exam, things like that. Because a lot of times they don't tell you specifically that they are strong acids. Okay, the first three are pretty easy to memorize. I'll put that back up there, so please don't freak out when okay, but the first three are very easy because they're kind of in a row or in a column on the periodic table is these three. Okay, so just keep that in mind. The key thing to remember is HF, and they do try to get you with this in some problems. HF is not a strong acid, okay? That's a very common kind of trick question they like to put on there, okay? Because a lot of students say that, hey, the halogens are going to be our strong acid, but HF is a special one, so it's not going to be a strong acid, okay? So it's going to be these three. And then after that, you got some, that just gives you four to really remember, okay? And I believe these are polyatomics that you're supposed to memorize: NO3, ClO3, ClO4, and H2S and SO4. Okay. And again, these are basically characterized as strong acids because they completely ionize, they break apart completely. So the arrow that we use to describe the reaction is going to be one way. Okay, it doesn't go backwards. It's not reversible. All right. Okay, so if you guys are good, can I move on? Everyone got that down? Okay, so this is all the stuff that I was talking about. Okay, so strong acids, you are actually going to like strong acids a lot more than weak acids because they completely dissociate, which means it's very easy to calculate pH and H plus concentration. So like I said, they completely dissociate. So let's take a look at 12.19. We'll do this one together just so I can show you guys how they work. So if you have HClO4 in a solution, okay, it's going to be aqueous because obviously it's in solution. And it's going to break apart completely into its ions, okay? So it's going to break apart completely. So what's the first ion that's going to come out of this compound? H plus, yeah. Acids release H plus, right? And what's going to be the state of matter? What do we put in the parentheses? Yeah, aqueous. It's dissolved in water. I'm not trying to trick y'all. And then obviously that means the anion, ClO4, for perchlorate, is going to be your other ion. Okay, so it breaks apart completely inside of solution. That's the key thing to remember. Okay. Whoa. Okay, now it tells us that the concentration is 0.04 molarity for our strong acid. Okay, now the reason why strong acids are really nice is because they break apart completely, which means they're going to maintain their mole ratio. So you see how it's 1 to 1 to 1? Okay, that means that when you have this solution concentration of the strong acid, you're going to have the same concentration for your H plus, and you're going to have the same concentration for your anion, your conjugate base. Okay, that's why strong acids and strong bases are so nice. They maintain their mole ratio. When we get to weak acids, where they don't dissociate completely, they're not going to have their one-to-one relationship. So you'll have to do a little more math to figure that out, which will be a lot of fun. I know, I'm super excited too. And I'm so excited. I love math. Anyway, okay, so if we calculate the pH, very easy. We just do negative log, and then the concentration of H plus, so 0.04. And this is why it's really helpful to memorize the strong acids, because if you had a problem like this on your homework or your test or the AP test, if you see the concentration of a strong acid and it asks you to find the pH, very easy. You can just be like, oh, I'm just going to put that in there, and that'll give me the pH. That's why knowing the strong acids are very useful. Okay, so the pH, and I'll just give you guys the answer, is going to be about 1.4. And this checks out because if this is a strong acid, right, the pH should be acidic. Okay, if you got a number greater than 7, that means you know you messed up somewhere. So a lot of redundancies to figure out if you did the math correctly, your calculator screwing up or whatever. Any questions on that? Pretty easy. Okay. All right, so with that being said, I'm gonna give you guys about 2 minutes to try 12.20. 12.20, we're basically going backwards. I'm giving you guys the pH of a strong acid. I'll tell you guys that since we just learned it. HNO3 is a strong acid, has a pH of 2.34. I want you guys to find the concentration, so molarity of the acid, okay? So find the molarity of the acid, and again, this is a strong acid. Take about 2 minutes to do that. Okay, so you guys should identify that you need to use the pH equation because they give you pH, and you're looking for the concentration of the acid. Okay, so the pH equation allows us to find the concentration of H plus. Okay, so 2.34 is equal to the negative log of H plus. Okay, now we can move the negative to the other side. Okay, and then since we got a log, we can get rid of it by doing 10 to the power of. So these will cancel out. So the concentration of H plus is going to be equal to 10 to the power of negative 2.34. Okay, and that's going to give us a value of 0.00457, around there. Okay, now this is the concentration of H plus. It's looking for the concentration of HNO3. However, we know that this is a strong acid, so this guy dissociates completely into H plus and NO3 minus. So if we have the concentration of H plus, since it's a strong acid and everything breaks up, this is going to be also equal to the concentration of the acid. So that's going to be our final answer. Okay. Yay. Yeah, that's pretty much all you have to do. Appreciate your attitude. It's always very upbeat. Cancels out my negativity. Yeah, it's neutral. But I mean, I'm hydroxide, so I have to, you know. All right, so that's going to be strong acids. Let's talk about strong bases. Strong bases is the next part. So strong bases, the most common ones are the hydroxides of alkali metals. Okay, alkali metals are the ones on the first column of the periodic table, so not including hydrogen, right? Because HOH is H2O, it's water. So starting with lithium, these are going to be the strong bases. Okay, and the heavier alkaline earth metals. Okay, so this is important to keep in mind because they do try to trick you with some of these as well. So we're going to be looking at the heavier alkaline metals. So if you guys take a look at this, things like beryllium, magnesium, those are not strong bases. It's going to start with calcium. Okay, so that's one thing to keep in mind. Beryllium hydroxide, magnesium hydroxide are not strong bases. It's going to be the heavier ones. So these down here. Okay, usually barium's the one that they go down to, not radium. And so just keep that in mind. These three are the good ones to remember. So this column, the first column, and then the second column starting with calcium. Okay, it kind of looks like a toilet.
It's the state of Idaho.
Oh yeah, the state of Idaho, that works too, yeah. That's pretty good.
Thumbs up. Good one. Do you want to look it up again?
I've never seen.
It looks like a thumbs up. But that's
Oh, I see it.
Does look like. This isn't a real place. There's nothing there. It's just that's just woods.
Okay, but it's still a place.
It's not a
But
place.
it's,
This is fake.
it's you just said there's woods there.
Yeah, there are. There's nothing there. All I know is that there's potatoes there.
Yeah, where do you-
No, I'm just kidding. Idaho's actually really pretty. There's a couple hiking trails I want to go on there.
France. You're gonna import all our potatoes from France.
Not gonna eat French potatoes. All right. Anyway, yeah. So strong bases are very simple. Is basically the same thing as strong acids. They completely dissociate inside of solution. And so let's do 12.21 together, and then we'll move on. Okay. All right. So this question is asking us which one is more basic. You got two bases that have the same concentration. Okay, NaOH and barium hydroxide. Okay. Now let's take a look at the equations to figure out which one is going to be more basic. Okay. So NaOH is a strong base. So when it breaks up, what's the first ion? What's the cation that comes out of this? Na. Yeah, Na plus. Okay. And then the anion is obviously hydroxide. It's me. It's me. It's me. Hello. All right, so that's going to be the first one. Okay, now we got barium hydroxide. It's also aqueous. And then it's going to be Ba2 plus. It's going to be the cation. Okay, and then OH minus, right? That's it. Is it? What's wrong with the second one? Yeah, there's two. There needs to be two. Two O's. It's double trouble.
You don't want to.
Two O. You don't want two O's. Actually, no. Two O's is good. It's me and my wife. Who's this? And then baby. No, I'm just kidding. All right. So that's just make sure you guys are aware of that. Yeah. Thank you. I actually did not plan that one. Anyway. I'm trying my best, dude. Alkaline earth metals. Just keep in mind the second column ones will have two hydroxides, so they dissociate into two. So, based on this, we can look at the mole ratio to figure out a couple things. Okay, so both of these, the strong bases, have a concentration of 0.001 molarity, right? 0.001. Now, if you look at the first one for sodium hydroxide, it's a 1-to-1-to-1, right? So that means it's going to carry over to the sodium and the hydroxide. Okay, but when you look at the barium hydroxide, okay, what's going to be the concentration of the barium ion? Yeah, 0.001. But if you look at the hydroxide, you'll notice that the ratio is 2, right? So it's going to be 0.002. So even though these two bases have the same concentration, okay, because barium hydroxide has two hydroxides, which one do you think is going to be more basic, the top one or the second one? Yeah, the second one. This one is going to be more basic. And the reason why is because it releases double the amount of the hydroxide ions, okay? And if you really want to do the math, you're going to find that the pOH of this one, the first one, is going to be equal to 11, but then the pOH of the second one is going to be equal to 11.3. Okay, so barium hydroxide is a bit more acidic, or not acidic, basic, even if it has the same concentration as NaOH. Okay, so just keep that in mind. Did I tell you guys the barium joke yet? What do you guys do with the dead chemist? You bury him. Okay, let's move on to the next stuff now. Okay, so strong acids, strong bases, super easy, right? Complete dissociation. Okay, it's clean, it's nice and clean. You break up, you stay broken up, there's no drama. However, that's not, as you guys know, most relationships don't work that way, right? A lot of times you only partially break up and they get back together and they break up and they get back together and they break up. And it's very annoying. That's why Taylor Swift is so admirable. What breaks up is done, not going back together. Okay, so that's weak acids. Okay, weak acids are only partially ionized in aqueous solution. Okay, so here we have the difference between a strong acid where, if you take a look at the picture, I don't know if you guys can see it too well, all the acids is broken up. Okay, there's either H plus or A minus. It's either the cation or the anion. But if you look at this one, third one right here, or not third one, this weak acid one, there's some hydronium, there's some anion, but some of the acid still stays together. So it's like impartially broken up. Some of the molecules dissociate, but some of them don't dissociate. And so this makes it a little bit more confusing for us when we're doing the math, because we can't just use the mole ratios anymore because they don't completely dissociate. Does that make sense? Now, basically, not all of the acid molecules break apart. Only some of them do. Okay, so if we wanted to write that as a in the chemical equation, you'll see, this is why it's called equilibria. You'll see that we have a reversible reaction. And so what we need to use now is the equilibrium constant, the Ka, to figure out, I know it all comes together, right? To figure out how much it dissociates, okay? So Ka is just K, but for acids. Okay, so everything from there is the same. It's just products divided by reactants. It's all the same stuff we've been talking about for equilibrium. All right, so a couple things before we move on to the math part. Okay, so if an acid is stronger, right? Which side of the equation does it want to go towards more? Right side or left side?
Right side.
Right side, yeah. If it's stronger, it wants to dissociate. It wants to break up, right? Okay, the stronger the acid, the more it wants to break up. So it goes towards the right. Okay, so if the strong acid wants to go more towards the right, what's going to happen to the Ka value? Is the Ka value going to go up or is it going to go down? It's going to go up, yeah, because Ka is products divided by reactants. I know, it's almost like it's all planned. I know, it really is. Okay, so just keep that in mind. Okay, stronger acids, okay, they're going to have a higher Ka value than weaker acids. Okay. Okay, now I use the term stronger because they're not strong acids. Just keep that in mind. It's weak acids that are just stronger than other weak acids. Okay. So yeah, so we're using the term stronger acids, but they're still stronger weak acids. So we're still talking about just weak acids. Okay. But there are stronger weak acids than other weak acids. Okay, so it's like a gym for weak acids. Okay, so there are multiple people working out. So this is the gym. Okay, my ex-girlfriend. Okay, so weak acids. Okay, so there are a bunch of weak acids hanging out in the gym. Okay, now this weak acid can bench 305. Beastly. That's amazing. Okay, so this is a pretty strong weak acid, right? That's a pretty freakishly strong weak acid. Okay, but this weak acid right here is still weak. Actually, maybe 305 is the wrong number, but it's still weak, but it's weaker. It can only bench 90 pounds. It's pathetic. Do you even gym, bro? Okay, and then this one right here is kind of is respectable. We'll give it a 200. You know, not at 225, which is kind of the benchmark for a strong person, but we'll say 200. Okay, So it's stronger, but it's still a weak acid. Because let's say a strong acid walks into the gym, right? Strong acid is like, it's on trend, and there's those people that can bench 500 pounds. So a strong acid is super duper strong, right? And these guys are, they're weak. Some are stronger than others, but they're still weak acids relatively. So that's my analogy. Okay. Does that make sense?
If you get that as like strong acids are like completely determined in order to weak acids are like kind of.
Yeah. These guys are like, gym is my girlfriend. I'm there 7 days a week. This guy's probably there like maybe three to 5 times a week. This guy comes every January, fills up the parking lot. You guys know what I mean. I hate Januaries at the gym. Okay. Call them resolutioners. Take up all the spots. What's up? Oh, okay, for sure. All right. So we got some examples right here. So just if we take a look at this table, you'll see again, some acids are stronger than some weak acids are stronger than other ones. So these guys are all weak. Okay, they're all weak acids. Okay, but if you take a look at them, they have different Ka values, so they dissociate at different rates. Chlorous acid right here, times 10 to the -2. So it's still relatively a stronger acid. This guy's the guy that benches like 305, right? This guy right here, a bit weaker. It's still a weak acid, benches like 200. This guy benches like 130. This guy's like just bar.
Are you gonna use this for everything?
Yes. If it takes, not that it takes longer, but if it dissociates less, the percentage that dissociates less. Exactly. It's like the ratio. Yeah. What's up?
If we were like writing temperature something about that, would it be fine to just talk about like the acid is stronger than like the conjugate acid?
Like talk about weak acids. You can just say it dissociates relative to another one. So like, let's say you were comparing these two acids, right? So like the first two, you're talking about these two, right? You would say that this weak acid dissociates more than this one because it is a stronger acid than this one.
So like in a reaction, like explaining where equilibrium is.
Mhm.
Like if it's going to the right,
Mhm.
because like the acid over here, I guess the acid over here is stronger than like the conjugate acid that
Mhm.
comes from like that base.
Yeah.
So how do you say like Ka is greater than 1 and equilibrium goes to the right because the acid dissociates like more completely than the conjugate.
Okay, I get what you're saying. So yeah, we wouldn't, so you don't, well, okay, so when we said that it goes towards the right more, it doesn't mean equilibrium lies to the right. Okay, because if equilibrium lies to the right, that means Ka has to be 1 or greater than 1, right? Okay. But in weak acids, I think that's a good point. Thank you for bringing that up. In weak acids, if you notice, Ka is always less than 1. Okay, K is always going to be less than 1 in weak acids. Exactly. Most of it does not dissociate. Most of them stays as the acid. Only some of them break apart. That makes sense. Yeah, and we'll talk more about how to describe that stuff. But yeah, that's a great point. Thank you for bringing that up. In a weak acid, okay, so you might want to write this down. In weak acids, the Ka is always going to be less than 1. Okay, sometimes a lot less than 1. Okay. Thank you. I appreciate it. Should have mentioned that. Okay. And that just basically means most of the acid molecules don't break up. Most of them stay together. Yeah.
We just need to know, like, we just look at the Ks.
Yeah. The Ka is a good way to do it. Or like the H+ concentration, things like that. Yeah. And so if it's not one of the strong acids, you can automatically assume it's a weak acid. These specific ones? No, you don't need to know. Yeah. These are just examples just so you can see. Any other questions? First, what we have to do here is we need to write the equation for how this acid dissociates. Okay, so we have formic acid, so H2H, okay? And then since it is an acid, it's dissolving in water, it's going to be aqueous. But since it's a weak acid, it's going to be a reversible reaction, okay? So it's going to be at equilibrium. Okay, weak acids are in equilibrium. Okay, it's gonna break down into H plus. Okay. And then it's gonna be COOH minus. Okay, so this is going to be your equation. Okay, so a lot of times you're gonna have to figure out the reaction for weak acids, but it's really easy. Just take away an H, and that's basically your reaction. Okay. Ian, what do you need? Just take it over with you, dude. It's like distracting when you're walking back and forth. I feel like I'm like being attacked or something. Okay, so it gives you the initial concentration of your acid, right? It's 0.1 molarity. And then they give you the pH, which is 2.38. Okay, now, if we want to find the Ka, we know that Ka has to do with equilibrium concentrations, right? So we need to find the concentration at equilibrium. So what do you guys think we need to use in order to solve this problem? Yeah, equilibrium, but what do we use to find equilibrium concentration? Yeah, ice tables. Exactly what you said. Ice tables. Good job, baby. Okay. Sorry. Yes, but you're correct. Ice tables. I was a little caught off guard. Okay, so, but yes, that's absolutely correct. It's ice tables, okay? Okay, so we start with 0.1 molarity formic acid. So where should we put it on this? IC or E? I, exactly. I. Okay, 0.1 molarity. Okay, and since it is going to dissociate in your solution, what should we put for our values here? 0, yes. Wow. Amazing. 0. All right. So let's go to the change row now. So for the acid, what's going to be the change? Positive or negative? Negative. Good. Negative X. And then since these guys, they start with 0, you got to form them, right? So positive X, because the mole ratio is 1 to 1 to 1. I know. Is this PTSD, guys?
Yeah. I
Yeah.
actually like these people. I feel like it makes sense.
Oh,
Yeah, they make
I'm
sense.
glad. That means I'm not doing a good job. I need to confuse you guys more. All right, now we got our values here, okay? Now we don't have K, so we can't just leave it like this because we need to find Ka, but we don't have the value for X yet. However, we do have one thing that will help us find X. Okay, we have the pH. We know that the pH is 2.38. We know that pH is equal to the negative log of the concentration of H plus, right? So if we can isolate H plus, we can plug it into X, and then we can solve for Ka. You guys see that? Yes? Okay, so let's solve it together. Yeah. So we're gonna start off by isolating the H plus. So we're gonna get rid of the negative sign, move it to the other side. Basically what we did earlier, negative 2.38. If we want to get rid of the log, we need to put everything to 10 to the power. So 10 to the power gets rid of our log. So 10 to the power of negative 2.38 is going to be our H plus concentration. Okay. And so if we calculate that out, that's going to give us 4.2 times 10 to the negative 3 molarity. So X is going to be equal to 4.2 times 10 to the negative 3. Yes.
The pH obviously.
Yeah, the pH is going to be once at equilibrium. Exactly. Yeah. So if you want to jot that down, the pH is always going to be when you're at equilibrium. Okay. It's a good question. Okay, so from there we can start substituting the values into the table just so we have everything organized. We know that since this is also X, it's going to be 4.2. Why did I put minus? Times 10 to the negative 3. And then from here, we just need to do 0.1 minus 4.2 times 10 to the negative 3. Now, I'll do that calculation for you just to save you guys a little bit of time. But that's going to give you 0.0958. Okay. All right. And then from there, do you guys think you can find Ka? All right. I'll give you guys a minute to calculate for Ka, minute and a half. And then we'll go over, make sure we all got the same answer. Okay. So calculate for Ka from here. Okay, guys. So let's go over it. So this is the Ka formula. So products divided by the reactants. We don't need to worry about exponents though, because it's just 1-to-1 ratio for all of them. So I'm not gonna write it all down just to save some time, but you're gonna plug in 4.2 times 10 to the -3 for both of these. So if you wanted to, for the numerator, you can just square it and then just divide it by 0.0958. And that will give you a final Ka of 1.84 times 10 to the -4. Something close to that. 1.8 times 10 to the -4 is great. Anything around there. Okay. So that's basically how we can use the nice table equilibrium to figure out, the concentrations of weak acids. Okay, just with the pH. Okay. Make sense? You guys think you could try one on your own? Okay. All right. Let's go to 12.25. Now, this one right here, I'll help you guys at the start, and then that'll kind of help you guys out. Okay, so sometimes they might not even give you guys the formula. Okay, so if you guys take a look at this, 0.02 molarity solution of niacin. Okay, who knows what the formula for niacin is? Neither do I. Okay, so that's the formula. That's going to be niacin. But we know that it says that it has a pH of 3.26. So just by that, we can tell it's a weak acid, or it's an acid. And it's not one of the ones we know, so it's probably a weak acid, right? So just based on that, we don't even need to use the formula. We can already come up with a reaction. Did you have a question? Or point?
No, I was just thinking,
Okay.
because 3.26 is an acid,
Yes.
but why is the weak acid?
Because it's not one of the strong acids you have to memorize. Yeah. Yeah. Usually, just for reference, I think HCl is one of the first ones that shows up on the pH scale, and that's around a pH of about 1. Yeah. So that's where your acids start getting into strong acid territory. And so if it's something higher than that, you can automatically assume it's a weak acid. Also, you don't have to memorize niacin. So when you do the equation, super easy, we can just write niacin. Okay, and since it's a weak acid, we know the reaction is reversible. It's at equilibrium. Okay, what's the first thing that comes out of an acid? Yeah, H plus. So we know H plus is going to come out of it. Yeah, and then for the second part, you can write whatever you want for the second part. I'm just going to write conjugate base, just because that's the technical term, conjugate base minus sign. If you want to write niacin minus H negative whatever, you can do that too, whatever you like. Okay, but this is basically the equation that you can write. So if you don't get the formula for the acid, don't freak out. If it's a acid, you know it's going to dissociate with an H plus, so we can just write the reaction like this, and then you can set up the ice table from there. Yeah. Yes, because you're just getting rid of one H plus. Yeah. Yeah. It's a good question. Yeah. So for these, you can just do 1-to-1-to-1 because you're just taking away H plus. Okay. All right. So I will give you guys about 5 minutes to finish this up. See if you could find acid dissociation constant, and if you forgot what that is, that's the Ka. Okay, so very similar to what we did before. The trick here, though, is identifying that even if you don't have the formula, just knowing that you're just getting rid of H plus. All right. So take about 5 minutes to solve that out. You'll need your ice table, and then we'll finish it up together. Okay, guys. So I have the answer up there on the screen for you. Something around 1.55 times 10 to the -5 should be your Ka. Guys, good with that? Easy peasy. Okay, so I did skip a couple steps in the, what is it? The solving, calculating, but it's squared because it's x times x squared. X is 5.5 times 10 to the -4. So you can just do it like that. The most important thing is that you get your exponent correct. It's 10 to the -5. But if you get something around there, you should be okay. All right. Okay, let's go on to the last thing for today. And then I will get you guys out of here, kick you out of my class. Okay. All right. All right. So next one is percent ionization. Now this is very simple. We probably talked about, we talked about percentages and things like that before. So we said that Ka tells us the strength of a weak acid. Okay. So Ka is one way to talk about how strong or weak an acid is. Okay. Another way we can talk about it, and I think this requires a little more work for calculation, but it kind of gives us a better mental picture because we're all comfortable with percentages. But we can also talk about acid strength in terms of percent ionization. Okay. So the key here, Whoa, what just happened? Okay, the key here is that the higher the percent ionization, okay, if it is bigger, that means it is a stronger acid. Okay, which makes sense because it breaks apart, it ionizes more. So the higher the percent ionization, the stronger the acid, and then obviously the reverse is true as well. The lower the percent ionization, it is a weaker acid. Okay, so just keep that in mind. Okay, the stronger the acid, or the higher the percent ionization, the stronger the acid, and the lower the percent ionization, the weaker the acid is. Okay, now again, it is stronger, it doesn't mean it's a strong acid, and it's weaker. These are both talking about relative with the weak acids relative to each other. Okay, does that make sense? Okay, so based on what we've learned, let's say I say there is a strong acid. Okay, what is a strong acid's percent ionization? Yeah, basically 100%. Okay, so really close to 100%. Okay, so just keep that in mind. Strong acids have about 100% ionization. Basically, almost everything dissociates. And then from there, we go into the weaker ones, which are percent ionization. Okay. All right, and it's very easy to find percent ionization. Basically, it is going to be the concentration of H plus at equilibrium divided by the initial concentration of the acid. Okay, so do you guys still have 12.29 on you? Somewhere you can look at the numbers, the previous problem?
Yes.
Yes, okay. So we'll use that as our example and we'll kind of close up from there. But if you guys take a look at 12.29, what was the initial concentration of your acid? Yeah, it's gonna be sorry, 0.02. Yeah, 0.02 molarity. Okay, everybody see that? That's the original concentration of niacin. Okay, and so this tells us what we start with, but then the numerator, we're gonna be talking about how much H plus is produced from your acid. So what's the concentration of H plus that we found at equilibrium? Yeah, about 5.5 times 10 to the negative 4, right? So that was the Ka. This is the concentration on your ice table, the equilibrium concentration. Yeah, make sure you guys keep those numbers straight. But basically, if we want to find the percent ionization of an acid, all we need to do is divide how much H plus it makes at equilibrium divided by how much it could have made. So potentially we could make 0.02, right? If it was 100% ionization. But since weak acids don't dissociate completely, we have to use what is actually produced at equilibrium. So take about, I don't know, 30 seconds to calculate the percent ionization of niacin in 12.29. So we're calculating for the percent ionization of niacin from the previous problem. And you guys should get about, or you should get like exactly 2.75% ionization. Okay. Obviously, if you use a different value, like if you use like 5.48 here, then it'll be a little bit different. But as long as you're around 2.75, you should be good. Okay, does that make sense? Okay, so what this is telling us is that in niacin's case, only 2.75% of the acid molecules breaks up into H plus and yeah, it is very low. So weak acids are very, they don't ionize a lot, which kind of gives you a frame of reference for how much strong acids dissociate, right? It's 50% or 50 times more. Okay, so just keep that in mind. All right.